Good morning, everyone. On behalf of management, principal, HOD, and faculty members of Mohammed Sadaq AJ College of Engineering, I take this opportunity to propose the welcome speech. The speaker for the day is Dr.K.Mariammal. She is currently working as Associate Professor in Department of Electronical Engineering, Madras University of Technology, Anna University, Chennai. She held the position of lecturer in the Department of Electronic and Communication Engineering. She received her BE in Electronic Communication Engineering, ME in Communication and Network, PhD from Department of Electronical Engineering from Anna University. She has also organized several faculty development programs and published many papers in conference and journal. Her research interest includes VLSI digital signal and image processing, multi-rate signal processing, and low power circuit design. It is an honor for all of us to have you as our chief guest, ma'am, and I welcome all the faculty members. Now I invite Ms. Dr. Mariammal to take over the session. Thank you.
Thank you, ma'am, for your nice intro. I'm unable to share the content. Do you have to give sharing access, or can I share it as such, sir?
Ma'am, you can share.
Okay. Now is it visible, sir?
Yes, visible.
Yes. So happy morning to all. Once again, I thank the organizers as well as the head of the department for giving me this wonderful opportunity. So the topic assigned to me is combinational and sequential circuits. So now before entering into combinational and sequential circuits, let me give a few intro about electronics. Then we move on to combinational and sequential circuits. The overview of this presentation goes like this. Followed by introduction, we will see combination logic circuits and sequential logic circuits. In combination logic circuits, we have several approaches of CMOS implementation, which includes complementary CMOS, ratioed logic, fast transistor logic. Similarly, dynamic CMOS, we have dynamic logic, along with some of the issues we will also see. And apart from that, we will also see the sequential logic circuits. So let us enter into the basic electronics. So we know the electronics is an art of science in which the motion of electrons takes place by applying electric field or magnetic field. And the electronics, we know the era started from vacuum tubes. Later we had transistor. Nowadays we have integrated circuit chip. So our eras goes from vacuum tubes to VLSI era. So all these electronic equipments, we are using it in our day-to-day life applications like electronic gadgets, home appliances, computers, transport systems, cell phones, cameras, and television, etc. And the vacuum tube, if you take, initially it was taken with the professor, the so-called Thomas Alva Edison in the year 1883. He has identified that electrons can travel from one conductor to another. So that effect, we call it as Edison effect. And following the Edison effect, John Fleming in the year 1897, he has discovered the so-called two-terminal diode. You can able to see the photograph of a diode. You see how big is this. And next we had Lee D. Forrest professor. He has again he utilized the concept of Edison effect, and he identified triode device, which is a three-terminal device. Apart from anode and cathode, we have additionally grid device, and this triode was instrumental in performing amplification as well as transmission of all kinds of energy. And when you compare vacuum tubes, they are larger in size, they are bulky, they are very fragile, they consume very high power. But nowadays we have integrated circuit chips, they are very simple in size, right? And so So in the transistor era, if we take 1948, we have three famous scientists you might have heard: John Bode, Walter Brittain, and William Shockley. They have received one Nobel Prize in the year 1956 for the invention of a basic transistor. This is the basic transistor. It is a crucial model which includes the three terminals: base, emitter, and collector. All these three scientists are from AT&T Bell Laboratories. And the transistor era, initially we had a single point contact transistor. It was first proposed by the three famous scientists. Then we had monolithic based transistor. Then later we have germanium as well as silicon based transistors are evolved in the electronics industries. And all kind of transistors are compact and they are light in weight, they are having low cost, and they offer very low power dissipation, and they are also very fast, and they offer longer life. So this made a revolutionary change in the electronics field. So moreover, they also used in most of the communication application like AM radio, FM radio. Without tuned amplifiers, we cannot construct the so-called AM and FM radios design. So the evolution of transistor started from Shockley's. So 1948, we had junction transistor, and it came into the commercial production in the year 1950. Later we had JFET and MOSFET, right? So without JFET and MOSFET, we cannot construct digital logic circuits as well as analog circuits. So JFET and MOSFET, they have invented in the year 1951 and to 1958. They are very reliable devices and they are powerful. And Professor Kilby, he is from Texas Instrument. He has invented the transistor in the monolithic circuit. And these two famous companies, Fairchild as well as Texas Instrument, they have commercially produced integrated circuit chip. And this is a photograph of Professor Kilby, right? He has analyzed initially the integrated circuits. So ICs, normally we know it is having several thousand components, or several thousand transistors are packed inside a single chip. It has three classification basically. One is small scale integration, medium scale integration, and large scale integration. Small scale integration consists of very few number of transistors, whereas medium scale we have higher than around 1,000 number of transistors, and large scale integration we pack millions and millions of transistors inside a single wafer. And the history of electronics goes like this. And apart from transistor invention, you might have heard Professor Hertz. So Professor Hertz, he has conducted an experiment on which he has identified the generation of electromagnetic waves. So normally we prefer the unit of frequency is hertz, right? So the name is invented from Professor Hertz. And 1894, Professor J.C. Bose, he has identified the propagation of radio waves, right, in the especially electromagnetic waves mediated through the space. So JC Bose, he is 94 years old. Recently he has passed away in the year, I think February 2023 he has passed away. And later we had Professor Lawrence. He has also postulated the existence of electrons. Then we had Professor J.J. Thomson. They have experimentally verified the existence of electrons. Then we had Fleming diode, triode, transistors, monochrome television. So all these classifications are set by specific standard. The standard, we call it as IEEE standard, Institute of Electrical and Electronics Engineers. For all kind of applications like networking, communication, 4G, 5G, 6G, all kind of application, they will give a certain standard. So we have to follow the standards and protocols offered by the IEEE. And evolution of integrated circuit chips, you can see the photograph. In 1950s, we have only one transistor in a single chip. Whereas 1960, you can see more than 16 transistors, that is transistor logic, are equipped with a single chip. And 1970, we had 8-bit microprocessor. It is having around 4,500 transistors. And 1980s, we have 32-bit microprocessor. It is having around 2,75,000 transistors. So likewise, if you see, as the year grows, the transistors count is also increases. So now, if you look into the microprocessor era, in 8-bit microprocessor, we have 4,500 number of transistors. And later we have 32-bit microprocessor, we had 2,75,000 microprocessor. Nowadays we have i7 processor, Pentium processor chips are available. Now all those things, if you see, the number of transistors are mainly decided by the so-called Moore's law. Moore's law. So Moore's law states that the transistor density doubles every 1.5 years or every 2 years. So Moore's law, it is a very, very important concept as far as our CMOS VLSI design is concerned. So we also have ultra large scale integration. So we can pack more and more number of transistors, which includes many functionalities. In our real life example, we can say mobile phones. So the CMOS integrated circuits, we may have analog CMOS integrated circuits, or we may have digital CMOS integrated circuits. So analog CMOS integrated circuits, if you take, we may have a single and multi-stage design. We may have differential amplifier. These are some of the examples of analog CMOS integrated circuits: current mirrors and operational amplifiers, oscillators, phase lock loop. These topics you might have heard from Professor Rasavi, Bensad Rasavi, analog CMOS integrated circuit design. And likewise, if you come into the digital part, we have the so-called famous author, Digital Integrated Circuits by John Rabe, right? He has given excellent book, right? So in which, if you refer, you have inverters, combination logic circuits, sequential logic circuits, arithmetic blocks, memory, and array structure. So these parts are the major parts involved in CMOS digital VLSI design. So now, the leading examples, if we consider Intel Pentium 4 processor, you just have a look at it. You can see Intel Pentium 4 processor consists of 55 million transistors, whereas the IBM 390 microprocessor consists of 47 million transistors. And what happens to the device dimension as well as supply voltage as well as frequency, let us see, simply analyze. Only up to 2014 this tabulation is shown. You can see here in the year 2002 we had 130 nanometer technology. 2014 we had 35 nanometer technology. Now we are at 2023. We are having 13 nanometer technology, 7 nanometer technology. At present 3 nanometer technology is in research in IIT. And if you see function density, that is transistor function density or DRAM capacity, if you see, 2002 we have that is 400 million transistors. Now 2004, that is 2014 we have 16 billion transistors. So the year grows, as the year grows, the transistor density also increases, as well as DRAM capacity, memory capacity shall also increases significantly. Now the major thing, whatever circuit we design, we should mainly focus on supply voltage, right? Supply voltage, because supply voltage mainly implies the impact the speed of operation, or we can say power dissipation. So because we normally have two power dissipation, static power dissipation and dynamic power dissipation. Static power dissipation, basically we write simple V into I, whereas dynamic power dissipation, we write CV square F. Power dissipation is CV square F. It is a proportional to load capacitance or parasitic capacitance, proportional to the square of the supply voltage, proportional to the operating frequency. So when the supply voltage increases, what happens? Power dissipation also increases, which will damage the device. So whatever device technique we propose, that should reduce the supply voltage. So 2002, we have supply voltage of around 1.5 volt. Now 2014, for this example table, it has been given with 0.6 volt. So obviously power consumption is also reduced. So you can see the some of the latest research work. So test chip has been produced in IIT with 3 nanometer technology. It is not commercially available, not in market now. So still research is going on in reputed institutions. And now when you design MOSFET based circuits, we have to think of the effects. The major effects includes decreased that is you can see decreased switching speed and increased leakage current, large subthreshold voltage swing, and we also have short channel effects, and the device also offers lower reliability. But we have to overcome all these difficulty. The solution we can go for is we may use FinFET devices, and we may use tunnel field effect transistors, junction field effect, that is junctionless field effect transistor, JLT, not JFT, junction less transistor, and carbon nanotube transistor, nanowire field effect transistor. If you take research papers, all these topics are still in research. So several authors are proposing newer techniques still. Now, the emerging issues, normally we talk about power consumption, memory bandwidth, latency, transistor count variability, and power management as well as thermal power management, multiprocessor communication, reconfigurable architecture, design for verification as well as testing, which includes modern system design. So these are the emerging issues. Now, innovations, whatever innovation we need, that should be incorporated in the designed architecture. So the architecture should be scalable, it is reusable, we should have reliable system architecture, we should have deployment and integration in real time, and we should also have on-chip interconnection. Memory hierarchy should also be taken into account. So all these components are taken into account to design an optimal VLSI circuit chip. Now, after this, initially I have given simple intro of what is electronics, what is VLSI, and how far it is going. So, as far as VLSI field is concerned, we should basically talk about 3 components: area, power, and delay. So, there is always a trade-off between area, power, and delay. So, we have to propose appropriate approach to compensate the trade-off. Now, let us enter into the first classification, combinational logic circuits. So, combinational logic circuit, before entering into the specified combinational logic circuits, let us have the comparison of combinational logic circuit and sequential logic circuits. You can able to see the simple pictorial representation. Rather than theory part, if you show some pictorial form, it will be very easy for you to understand. So, combination logic circuit, you see, it is the output is a function of only present input, only input. Whereas if you see the sequential connection, sequential logic circuit connection, apart from combination logic, we also have a feedback wherein the state is stored in the register or memory. So we have a feedback, right? So we can say the combinational design is a non-regenerative circuit, whereas sequential circuit is a regenerative feedback circuit, because output is the function of present input as well as previously generated inputs from the respective output. So, for a combinational circuit, we don't want any memory to store, whereas for a sequential circuit, we need a memory to store in a particular register. So this is a simple classification of combinational and simple difference between combinational circuit and sequential circuit. Now let us enter into the combinational circuits. The combinational circuit, we have 2 categories. One is static CMOS, another is dynamic CMOS. Right now we are talking about static CMOS in this presentation, in this present slide. For a static CMOS, at every point in time, you can able to see the blue colored highlighted line. Gate output is connected to either VDD or VSS. So output is either connected to supply to output supply, or it may be connected with the ground. So there are 2 options. So always we have a low resistance path exist between output to ground or the so-called we supply to output, right? So this is one important point in static CMOS configuration. And always the static CMOS configuration assumes the values in the form of Boolean representation. So it is like a Boolean function. So in contrast with static CMOS, when you go for dynamic circuit wherein we talk about temporary storage of signal values on the capacitor. So dynamic means immediately the value should be keep on refreshed. So in order to refresh the corresponding values, we need to have a capacitor. So dynamic CMOS, please do remember the capacitance. We do have a capacitance because capacitor charges and as well as discharges. So temporary storage is needed in dynamic circuit, whereas static CMOS it is not required. Now, if we consider a simple static complementary CMOS circuit, complementary means obviously we should have P-channel MOSFET, PMOS and NMOS. Remember, P-channel MOSFET always the majority carriers are holes. For N-channel MOSFET, majority carriers are electron. Of course, both MOSFETs are the unipolar devices. It is not bipolar. Both of them are unipolar devices. So here static complementary CMOS configuration, we have both PMOS as well as NMOS. So PMOS devices, we call it as pull up network, and the NMOS devices we call it as pull down network. Always please do remember, always the pull up networks are connected at the top, that is PMOS is connected with the supply voltage, NMOS is connected with the bottom side, or it is in turn connected with the ground. And when we draw equivalent circuit implementation, they are of course dual in nature. So pull up network and pull down networks are dual in nature. They are also called as dual logic networks. Now, one example you can see here, NMOS transistors. Right now, we are talking about static CMOS configuration. Static CMOS indicates complementary, both N and P should be present. So when you consider this NMOS arrangement alone, NMOS transistors in series and or parallel connection. So now transistors, we can say it is like a switch based on the K terminal input, it may close or it may get open. So NMOS switch closes when the switch control input is high. You see the two configuration here, only two NMOS transistors. So here the classification is there is no bubble at the gate terminal, so we can call this as NMOS. We should know the symbol of NMOS. So here we have the so-called we don't have any bubble, so it is a simple NMOS. Two NMOS transistors are connected in series, and wherein A and B are their inputs, right? Whenever A and B are high, our output side Y equal to X. The X is simply transmitted to Y. So this we can call it as simple series connection in NMOS transistor. Now, you can also say it is it performs Boolean AND operation. Boolean AND operation. Whatever combination if you put for 0 case, your answer is 0. 1 case, your answer is 0. 1 case also 0. 1 case, you get answer is 1. So it is a AND operation. A series connected NMOS transistor performs AND operation. Likewise, when we connect the two transistors in parallel, so what happened? They perform OR operation. So if A equal to 1, A equal to 1, Y equal to X. If B equal to 1, Y is equal to X. So even one of the transistor is on, output is equal to X. So you can say the OR operation consists of parallel NMOS transistors, and operation consists of series connection of NMOS transistor, because this is needed for realization of complete pull down network as well as pull up network. Especially pull down network is consists of NMOS. So to implement any Boolean logic function pull down network, we want the respective configuration for NMOS transistor. So however, the NMOS transistors also pass a strong 0 but a weak 1. So strong 0 means, so if you take the previous slide, previous slide. So here NMOS transistor, bottom network is an NMOS transistor. So suppose assume the F, output F is at logic high. When all the inputs are high, pull down network enabled, so it goes to ground. All the output goes to ground. So what happens? It passes these all components to ground. So we can say it is a strong zero component. So NMOS transistor pass a strong zero but a weaker one. So later example you will come to know elaborately. Now you can see again, like NMOS transistor, PMOS transistors in series as well as parallel connection. You can see the PMOS switch closes when the switch control input is low. You can able to notice the bubble existence at the gate terminal. So bubble is present at the gate indicates a PMOS symbol. So when A is high, PMOS should be off. Always for a PMOS, input should be off, input should be low to get on. So when A switch is high, then PMOS is off. B switch is high, PMOS is also off, right? So it performs, you can see an OR operation, A plus B the whole bar. A plus B the whole bar, or you can say NAND operation. NAND operation. So A bar and B bar. So likewise, you can see the parallel combination of PMOS transistors. Parallel combination performs NAND operation. So one performs NOR operation, another performs NAND operation. Its equivalent Boolean expression shall also be given. So you can check with the AB all four combinations. Since we have two inputs, there are four possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. For example, in the second configuration, parallel arrangement, if you take AB whole bar, when we take A equal to 1, B equal to 0, B equal to 0, then what happens? We get 1 into 0 whole bar. So our answer is 1. So one of the transistor passes the input to the output side, right? So we can say the PMOS transistor pass the strong ones but a weak 0. So PMOS transistor always passes a strong 1. NMOS transistor always passes a strong 0. So PMOS transistor like NMOS, PMOS transistor, if you see the previous diagram, here PMOS transistors are connected with the pull-up configuration. So this VDD is connected with the output via the PMOS configuration. So we can say it passes strong ones. Now, when we consider the respective threshold of PMOS as well as NMOS network, you see here the pull-up network always PMOS, pull-down network is always NMOS. So here, when we take the respective terminals, you see the source and drain terminals for a PMOS. Source terminal is connected with VDD. For an NMOS, drain terminal is connected with VDD. Please make a note of it. The source terminal of source terminal is connected to VDD. For an NMOS, drain terminal is connected with VDD. And you can able to see here, the gate terminal of a PMOS is connected to ground. So it is having gate voltage excited with the gate voltage very low value. So PMOS device turns on. So PMOS device turns on. So it passes, that is, this switch gets closed. This switch gets closed. So VDD is passed through the output side. VDD is completely passed to the output. Earlier, it was like 0. Now, upon turning on the PMOS transistor device, it charges up to VDD. So initially the charge stored on the load capacitor is 0. Now when the transistor PMOS transistor is turned on, it is having the maximum value of it is charged, and it is having the maximum value of VDD. So this is one arrangement. Now if you see the second arrangement, the same thing, we are having NMOS instead of PMOS. Here we have NMOS. NMOS, to turn on NMOS device, we should give high voltage. So we are exciting this with a VDD voltage. So this makes the NMOS transistor turn on. So what happens when the NMOS transistor turns on? Again, it is a switch. It will pass the signal to the output. It will pass the voltage, VDD supply voltage, to the output side. But the NMOS, as I mentioned earlier, NMOS allows strong zeros, but a weak one. So weak one means weak supply voltage. That means instead of VDD, here you see PMOS maximum voltage is VDD, but here NMOS, if you see maximum voltage, that is charged in the load capacitor is VDD minus VTN. The threshold voltage drop is also taken into account. That is the major thing. Therefore, we are telling that it is a weak function of 1. NMOS device passes a strong zeros, it is a weak ones. So instead of VDD, it is having VDD minus VTN. One drop, of course. If I have a threshold voltage of, let us say, 0.4, my supply voltage is, let us take 1.5. So obviously maximum voltage I can get here is 1.5 minus 0.4, I get only 1.1. So that is one thing. Now coming to the next bottom arrangement. Again, bottom arrangement, you see the pull down arrangement, pull down network, we have the so-called NMOS configuration, whereas this is our always PMOS is pull up, NMOS is pull down. Crosswise you think of. These two are pull up network, these two are pull down network. Now, the bottom two arrangements, if you see, the output to ground connection. Earlier we had supply to output, both cases supply to output. Now this case you consider output to ground. Output to ground, we are connecting the so-called NMOS switch, as well as output to ground we are connecting so-called PMOS switch. So what happens, let us see. So here the output capacitor CL is charged initially with VDD. Now to discharge it to 0, what we should give, we have to give the excite high input voltage at the NMOS terminal. So when we give high input voltage, NMOS devices turns on. So this switch gets closed. This switch gets closed. Whatever output exists here, all of them will go to ground. So it is discharges from maxima to minima. Let's say maximum VDD to minimum 0. Now you can see it completely vanishes, and finally we reach 0. So therefore, we call NMOS devices pass a strong 0, not 0.5, not 0.7, like this. Directly it goes to 0. So for digital CMOS, this point is very, very important. NMOS device passes strong zeros, PMOS device passes strong ones, right? Now coming to the fourth arrangement, this arrangement, it is a PMOS configuration connected between output and ground. This is output. The capacitor CL is initially charged to VDD. Now we are giving gate terminal of a PMOS transistor with the ground. What happens? This transistor turns on. Now this PMOS device, what happens? Since it is on, capacitor CL discharges. Capacitor CL discharges, but you can able to see it is not reaching 0. We should have some threshold voltage, that is VDD to VTP. For example, if I have minus 0.4 or PMOS, we have negative voltage. It depends on the types of MOSFET. We may have enhancement type MOSFET, or we may have depletion type MOSFET. So if we use enhancement type MOSFET, the threshold voltage shall be of negative. Depletion type MOSFET, the threshold voltage of positive. So here anyway, if you take magnitude, instead of reaching 0, it may reach some other threshold value. Maybe it could be a 0.4 or it could be a 0.3. So it is not passing strong. That is, it is a weak function. The PMOS is a strong. PMOS passes strong ones, whereas it is a weak function of passing the output to the ground. Right. So this threshold voltage drop variation is very, very important in all kind of circuit, digital circuit analysis. Now, when we take complementary CMOS logic style, the pull-up network, as I mentioned earlier, pull-up network is the dual configuration of pull-down network, because NAND can be taken with NOR, and OR can be taken with NAND. So you can see, remember the so-called De Morgan's theorem, A plus B the whole bar equal to A bar into B bar. Likewise, A bar B bar, AB the whole bar equal to A bar plus B bar. So dual option is also possible with PMOS as well as NMOS devices. So the complementary gate here is inverting. Now you can see AND gate. AND gate, we can realize the AND gate using one NAND gate followed by an inverter. Now let us see the complementary CMOS realization of NAND gate. Very simple. NAND gate we are realizing with complementary CMOS arrangement. As I mentioned earlier, NAND gate the bottom network is pull down network, top network is pull up network. The top network is pull up network, bottom network is pull down network. Always pull down network shall be of n mass, pull up network shall be of p mass. So here AB we have, right? AB whole bar is our NAND gate. So realization what we should do is, here is AB means we have to connect in series. And for a pull up network, very simple idea, dual. Here it is series means here you should put it in parallel, right? So AB are connected in series, here AB are connected in parallel. So you know very well the truth table of two input NAND gate. So right, corresponding function is also specified here. Pull up network F equal to A bar plus B bar, which is equal to AB whole bar. So you can also verify this with the help of corresponding input. For example, if I give A equal to 0, B equal to 0, both are 0. Both means here PMOS, both PMOS gets on. So we have output VDD, output that is this switch is closed, output is equal to 1. Output is equal to 1. Now you can able to see output is equal to 1 here, right? Whereas when I take A equal to B equal to 0, both NMOS are turned off. So no way, no path. No path exists from output to ground because both the switches are open. Now likewise, if you check the last case, 1, 1. If both are 1 means both the PMOS transistors. For logic high, both the PMOS transistors are in off condition. Both are off condition, so it is not having connection with the supply voltage. Whereas here bottom side, when I excite A equal to 1, B equal to 1, both NMOS devices are turned on. So we have a low resistance path exists between output to ground. Output to ground. So what happens? All the output will goes to ground. We have only 0. So logic 0 is output. So very simple. Yeah, we can able to realize any Boolean function with the help of the respective complementary CMOS configuration. Now you know to construct this NAND gate. To construct this NAND gate, we need 4 transistors, 2 NMOS transistors and 2 PMOS transistors. Likewise, we can take OR gate as well as NOR gate representation. NOR gate, you can able to see it is A plus B the whole bar. So to realize in a simple way, to realize it in a practical manner, what you do first, A plus B means plus means pull down network should be connected in parallel. Into means pull down network should be connected in series earlier, as mentioned earlier. Now A plus B indicates A and B are connected in parallel in the pull down network. So when it is connected in parallel, and the top, what you should do, you take its inverse dual. That is both A and B pull up networks are connected in series. So this makes your NOR gate operation. So here also you can verify with all 4 input combinations. Let us take first 0 0. 0 0 case, A and B are 0. A and B are 0 means we have both P channel MOSFETs are enabled, whereas here N channel MOSFETs are disabled. So output VDD is passed through the output side. We get maximum value of logic high 1. And can also think of third case. I'm taking case 3, 1 and 0. A equal to 1, B equal to 0. So A equal to 1, B equal to 0 means B equal to 0 means this transistor on, but A equal to 1, this transistor off. So it will not allow the output to reach VDD to reach at the output. So this line is broken. Now you can see here bottom side A equal to 1. So this transistor is enabled, B equal to 0, this transistor is off. So anyway, we have a path, 2 path from output to ground. One path is via A, another path is via B. B path is now broken, but A path is exist. So all outputs will go to ground. So what we have, output is 0. So this in this manner, you can write a NOR gate. So now complex CMOS gate, one more example is given. Now you can see the function D plus A into B Boolean function D plus A into B plus C whole bar. Now what you should do, B plus B means you have to connect B and C in parallel. B and C transistor always initially construct pull down network, and upon constructing pull down network, you can draw the dual of the pull down network as a pull up network on the top. So here B plus C, you can see plus indicates parallel combination. So B and C are connected in parallel. Then into A, into means multiplication. So in multiplication, you should connect the component in series. So A is connected in series. Now the entire term is connected with plus. So for the entire structure, you have to add parallelly one transistor D. For the entire structure, add one transistor D. So now what happens? Pull up network, you have to realize pull up network initially you can see D is in parallel combination. Now it should be in series. Whatever transistor is in parallel, those things should be in series at pull up network. Similarly, for a parallel transistor in pull down network, it should be in series in the so-called pull up network. Now since D is in parallel, here it is in series. Now you can see A uh, this A, B and C are in parallel. Here it should be in series. Again, B and C are series with A, but here B and C are series parallel with A. You see the very simple design. It is a complex CMOS gate design for the given um, Boolean function D plus A into B plus C the whole bar. Now you have 4 variables A, B, C, D. So 4 variable means you have 2 per 4 combinations, 16 combinations you can verify the output, right? You can draw the truth table and you can also verify the output. So the examination point of view, the truth table may be given means you should be able to construct the gate, right? Once truth table is given, from the truth table you have to convert, you have to string the Boolean expression, and for that Boolean expression you should draw the corresponding complex CMOS complementary logic gate. So now to implement this 4 input gate, how many transistors are needed here. You can see bottom side we have 4 transistor, upper side we have 4 transistors. So we need 8 transistor. We need 8 transistors. We can say it is a 2n number of transistor. To implement n input transistor, we need 2n number of transistors in general. So all the transistors design we can go with the cell concept. So we have a standard cell design which includes general purpose logic. It can be easily synthesized, and while we designing a standard cell arrangement, it should offer same height and varying length. And similarly, we can also go with the arithmetic based data cells. For regular and structured design, we go for data path configuration, which includes similar wiring in the cells, and every cell should have fixed height and width. Now, the static CMOS properties, you can able to see static CMOS. Simply, I have given the 3 examples. One is NAND gate, another is NOR gate, and the another is the so-called simple 4 variable based Boolean expression D plus A into B plus C the whole bar. Now, when we examine the properties of CMOS, static CMOS, they offer that is, they offer full rail to rail voltage swing. Rail to rail voltage swing, that is VDD to VSS. VDD to rail means peak to peak, we can call it as. So maximize plus VCD, VDD minimize my VSS. So rail to rail voltage swing is possible with this static CMOS. And when voltage swing is high, obviously noise margin is also high. So always for any better design, we need higher noise margin, right? So, and you can also see the logic levels does not depend on the relative device sizes. Logic levels does not depends on the relative device sizes. That is, we are not talking about device sizes here. We can say it is independent of device size. We can say this as ratio less. We can say this as a ratio less device. Complementary CMOS, it is a ratio less logic, right? And the examination point of view, 2 more questions may be asked like this: ratio less logic. And always a path exists from VDD to output or output to ground. It is in steady state. It is in steady state. I have mentioned the 2 concept. Always NMOS allows strong zeros, PMOS allows strong ones. So always low impedance path exists between either output to VDD or output to ground. We can say at a time only one of the transistor is in on condition. They are of course mutually exclusive. mutually exclusive. When one is on, other is kept off, right? They are mutually exclusive in nature. So extremely high input resistance, that is the other state will be in off condition, nearly zero steady state input current, because steady state only one of the transistor is non condition. Zero steady state input current is available in this static complementary CMOS arrangement. And you can also observe no direct path or no direct path exists between supply to ground, right? Supply to ground, no direct path exists, because at the time only one transistor either pull consists of some resistance. So propagation delay is a function of load capacitance as well as the resistance of the transistors. So basically we know we have to follow the Elmore's delay model 0.69 RC, right? So Elmore's delay model has been considered in general. So these are some of the basic properties of static CMOS circuits. Now, as I mentioned earlier, the transistors are considered as switch delay model. So switch delay model, that is, you take the simple NMOS transistor, switch delay model, the corresponding equivalent resistance is denoted as R equivalent. Now, the same NAND gate, same way we can draw a switch delay model for NAND gate, switch delay model for inverter, and switch delay model for NOR gate. So am I going very fast or is it okay? Hello, anyone can please respond? My speed is okay?
Okay, ma'am.
Okay. So switch delay model, you can see the three configurations: NAND, inverter, as well as NOR. So we are modeling every transistor in terms of their resistance and capacitance. Normally, time constant or the delay is we can represent in terms of 0.69 RC, Elmore delay model. So R here is equivalent resistance, and N resistance of pull-up network as well as pull-down network, and C here is equivalent capacitance of corresponding pull down as well as pull up network. So here CL, you can see CL is the capacitance connected at the output side, right? And C int is the parasitic capacitance present at the pull down network side. So likewise, you can able to draw the switch delay model for any circuit. Now, considering this simple NAND gate, you can see the delay is dependent on the pattern of the inputs. So, based on the input pattern, that is A and B, the delay varies, because accordingly we have varying resistor as well as capacitance. So, for low to high transition, both inputs go low. Low to high transition, both inputs go low. We can write it as I mentioned earlier, 0.69 RC. 0.69 RC. So you can see here RP is the equivalent resistance of a PMOS, right? Instead of R, here it is given as RP by 2. RP by 2. So RP by 2 means both inputs go low. Both inputs go low means both the inputs are connected. Both inputs are connected. So both inputs are connected means they are in parallel. Parallel combination of 1K and 1K is answer we get 0.5K. So likewise, here RP parallel with RP, we get RP by 2. Therefore, equivalent resistance is RP by 2. Right? So delay is 0.69 RP by 2 into CL. Now, if only one input goes low, means one of the resistor alone closes with the corresponding switch, other resistance does not create any connection. So what happens? We have simply 0.69 RP into CL. So analysis point of view, you have to consider all resistance effect as well as capacitance effect. So low to high transition, we have to think of low to high means higher output case. The pull down network is off, pull up network is on. So supply is passing through the output voltage. So low to high transition, you have to talk about the pull up network. Similarly, high to low transition, you have to talk about the pull down network or NMOS. So NMOS, you see, when both inputs goes high, what happens? Both are connected to ground, so we get low transition, high to low transition. Now in this case, we have two resistors, Rn and Rn. Two resistors, Rn and Rn. So what is the equivalent resistance? Rn plus Rn, because they are connected in series, so we have 2 Rn. 0.69 into 2 Rn into Cl. So in this way, we have to analyze the effect of delay. So depending on the input pattern connections, the delay varies. That is a major concern. Now, for various values of input patterns, you can able to see the photograph, that is a uh, graph indicating the corresponding voltage with respect to time. Now, you can see the three different graph on the right hand side of this graph. A equal to B equal to 1, that is for low to high to low transition. This case, it takes minimal delay. It takes minimal delay, whereas this brown color or like thick pink color offers very high delay. Right. So in this way, you have to analyze all possible input patterns. What is the delay incurred, that you have to check. The tabulation is also given for the respective graph. Now, next point is, apart from delay, we should also think of the transistor sizing. Transistor sizing normally done with reference to the CMOS inverter. CMOS inverter. So here you can see the transistor sizing are mentioned. Transistor sizing are mentioned here. You can see we have Rn and Rn, they are connected in series. That is pull down network. First I am telling. Here Rn and Rn are connected in series. So we have 2 Rn, right? We have 2 Rn. If we combine or if we compare this with the one CMOS inverter, the CMOS inverter size is Rn. Let us take CMOS inverter size is Rn. So to have Rn, that is, this resistance should be equal to Rn, inverter resistance Rn. So in order to equate this, what we should have, this should be Rn by 2, this should be Rn by 2. That is Rn by 2 plus Rn by 2, we get Rn. So the denominator we have 2, right? That 2 you have to take. This should be this size should be increased by 2, right? Likewise, you have to take. Again, here for a PMOS, let us take a PMOS. The PMOS, we have equivalent resistance. CMOS inverter resistance is RP. So we want RP. So in order to get RP, you can see it is in parallel, RP parallel with RP. So RP parallel with RP, we get, of course, half RP by 2. So the denominator 2 component you have to take here. So in this way, the transistor sizing is done. Basically, the transistor sizing is done with reference to the CMOS inverter. So once the CMOS inverter varies, obviously this sizing is also varies. So accordingly, the sizing is planned. So likewise, here also, here you can see pull-up network. The pull-up network is a PMOS, pull-down network is a NMOS configuration. So NMOS configuration here, equivalent resistances are N, right? Rn. So both are Rn. Both are Rn. So you can take denominator 1. Similarly, here we have, let us take Rp. It is 2 Rp. When you take denominator, again you get Rp by 4. So Rp by 4, denominator you should take 4. So it depends on the CMOS pull-up network specification, inverter specification, as well as NMOS pull-down network inverter specification. Now, transistor sizing, when we consider the four input gate for a complex logic gate. For a complex logic gate, you can see R equivalent, right? When you take the bottom network, full of network, Rn, that is Rn is simply Rn. So here only one resistor is connected, one transistor is connected, simply you put 1. Right now, here we have 2 transistors. two transistors, you take this path. This is one path and this is another path. So this path again you have to take Rn by 2 plus Rn by 2. So what happens? You get total Rn. Therefore, denominator 2 you have to add here, right? So in this, in a similar fashion, you have to write for PMOS also. For a PMOS, you get 4, 4. So 4, 4, what you get? 4, 4 means you get that is Rn by 2 plus Rn by 2. Rp by 2 plus Rp by Rp. If you take 2 Rp, you get denominator 4. Right. So likewise, you have to analyze the so-called PMOS sizing as well as NMOS sizing. Of course, it is not only this arrangement. You can take any combination if more number of devices are involved. For example, you can also take this way fashion. You can also take 6, 6, 6 and 6 and 3. Right. 6 and 3. Right. See here, 3 indicates if I have Rp by 3, Rp by 3, this should be Rp by 6, Rp by 6. When you add these two, you get Rp by 3. So this is equivalent to this time. So now we have to consider the fan in and fan out. So fan in here indicates number of input gates. Number of input gates. So number of input gates here, it is a 4 input NAND gate. It is a 4 input NAND gate. Now you can see for this, you can able to see bottom network is a pull down network, upper network is a pull up network. For this case, we have the propagation delay variation. That is when we increase the number of inputs, obviously number of resistance and number of capacitance shall also increase, which will degrades the propagation delay. So again, if we follow Elmore's delay model, you can see high to low transition. High to low transition, we talk about the so-called NMOS, that is bottom network. So you can see total equivalent resistances are equivalent and total capacitance is C1 plus 2 C2 plus 3 C3 plus 4 CL. You can see distributed RC model. We prefer Elmore delay analysis. So we have this time constant. So what happens? The propagation delay is very high because capacitance also increases, resistance shall also increases. So propagation delay increases means obviously speed comes down, right? So it is a worst case delay. So always when we design a circuit, we should take care of all these things. Now, when we draw propagation delay as a function of fan-in, the observation here is for lower number of input gates, propagation delay is almost linear. Whereas when we increase the number of input gates, the propagation delay especially increases quadratic manner. So the advisable number of gates used in the circuit is 4. That is, gates with a fan-in greater than 4 should be avoided in order to in order to avoid the propagation delay degradation. Now, fan out also, like fan in, we should also think of fan out. So fan out means related with the output side, number of gates connected with the output side. So all gates have the same drive current. Slope is a function of drive strength. So fan out also we have to think of. So as the number of gates increases, the propagation delay also increases in a so you can see fan in and fan out. Fan in, the quadratic increase happens due to the resistance as well as existence of capacitance. Fan out, we have each additional fan out gate add to gate capacitance to CL, like that is A1 into F1 plus it is like a formula. For every node, we have to consider this one. So A1 into fan in, A2 into fan in square, likewise A3 into fan out square. So that is a total propagation delay. So to reduce the propagation delay or to increase the speed of operation, we can go for several approaches. One such approach is transistor sizing. So transistor sizing, we can do transistor sizing, that is W by L, width and length we can change in order to reduce the so-called capacitance effect as well as resistance effect. Once R and SC reduces, automatically propagation delay also reduces, speed gets improved, right? And the another option is progressive sizing. Progressive sizing means you can see M1, M2, M3 and Mn transistors are available. So M1 size is little bit higher than M2, and M2 is little bit higher than M3. Again, Mn is the smallest size. So when we take progressively increase in the size, right, that also reduces the RC line constant, that is reduce the delay by more than 20% when comparing with the existing design, right? And another thing is, although it decreases the delay, you can able to see it decreases the gain as the technology shrinks. So technology here is normally, technology means 3 nanometer technology means we talk about length of the transistor. So when we resize, obviously it will affect the gain also. So based on the application, we have to think of all the parameter like area, power and delay. Now, the another example is so-called transistor reordering or transistor ordering. Instead of putting, you can see here M1, M2, M3. M1 is present at the bottom, M3 is present at the top, right? So here input 1 is excited with M1, right? So when we give low to high transition, the signal has to reach from this path to this path. That is, in order to charge the capacitor CL, it has to proceed with M1, M2, M3, right? Right, because output of M1 is connected with M2, output of M2 is connected with M3. Further, it is going to the respective capacitor. Then it is getting charged. So delay here is determined by the time to discharge capacitor CL, capacitor C1 and C2. All these three capacitors are involved, right? So the path, you can able to see the propagation delay path will be very high. So the length, particularly the length of operation will be very high. So obviously we can say the delay is high. So critical path delay is high. So in order to overcome this, what we can do is, you can see the similar configuration. Instead of giving input at M1, input is given at M3. You can see the variation. Input is given at MT. So only the delay is determined by the capacitor CL. Capacitor CL. So as per our equation 0.69 R into C, now CL is the only one component which minimizes the propagation delay. So in this manner also we can perform the delay reduction. And the alternative approach, we can see it is a logical restructuring. So logical restructuring, you can see it is a 8 input NAND gate. The first gate is an 8 input NAND gate followed by an inverter. Now it can be implemented using, now you can see 4 NAND gate followed by 2 OR gates followed by 1 NAND gate and OR gate. So same thing you can implement with restructuring so that the delay gets minimized, right? So yet another structure for this design, you can say instead of 2 input NAND gate, we can also go ahead with the 4 input NAND gate. So by doing logical restructuring also minimizes the delay. So, but when we do logical restructuring, of course, one point is delay reduction. Another point is what happens, the so-called, complexity. We are adding more and more gates. So complexity increases, right? And delay reduction, for example, one more thing that we can say, it is also used in glitch reduction. Glitch reduction means, if the signal should reach at the, for example, if I take this point, both input should reach at, both the signals should reach at the same time. That is, arrival time for the respective input should be at same time. For example, the signal arriving at this point is 1 second. After 1 second, signal arriving at this point is after 2 seconds. What happens? Obviously, this NOR gate should respond. NOR gate should respond only when both inputs arrive at the same time. Otherwise, there is a glitching occurs, right? So glitch reduction also done by logical restructuring. So now another approach is isolating fan in from fan out using buffer insertion, right? So fan in component and fan out components are isolated by inserting a buffer, which also minimizes the power to a significant extent. So another important thing is reducing the voltage swing. Reducing the voltage swing. So voltage swing here is normally we write 0.69. In general, we take that is 3.75. That is 3 by 4 CL into VDD ID SAT. That is saturation region current expression. Current expression. So in order to reduce the voltage swing, we need to reduce. That is when the voltage is reduced, propagation delay also reduce. So to reduce the voltage, what we have to do, you have to operate the device with a lower supply voltage. So when we reduce the supply voltage, obviously reduces the power consumption. That is good, right? But the thing is, we have to think of sensing amplifiers. Sensing amplifiers for providing appropriate voltage swing. So um, as of now, we have talked about what is a combinational logic circuit, particularly static CMOS. In static CMOS, we have gone through complementary CMOS realization. For realizing a complementary CMOS configuration, we want 2n number of transistor for n input variable design. Right, that is one idea. And the complementary CMOS configuration, pull down network is always NMOS, pull up network is always PMOS, and NMOS always passes the so-called strong zeros. PMOS always responsible for passing strong ones, right? And the propagation delay reduction. Propagation delay is a major concern. One of the major concern to reduce the propagation delay and to increase the speed of operation, we can go for several approaches. So few approaches we have discussed. Now, one more thing, the static CMOS, complementary CMOS, it is like a ratio-less logic, because we are not talking about any sizing is not a major concern, but the yet another approach is yet another yet another static CMOS configuration is ratioed logic. Right, static CMOS, one type is complementary CMOS configuration, and the another type is ratioed logic. Ratioed logic, for a very simple idea here is, why do we go for ratioed logic? Ratio logic is meant for decreasing the number of transistors or decreasing the complexity. So for a complementary CMOS, for 2 input we want 4 transistor, whereas for ratioed logic we don't want 4 transistor, we want n plus 1 transistor. Instead of 2n number of transistor, we want only n plus 1 transistors. So here you can see the pull down network. 3 arrangements are listed here. The goal is to reduce the number of devices over complementary CMOS. The mathematical representation is complementary CMOS, we want 2n number of transistor, 2n number of transistor, whereas for ratioed logic, we need only n number of transistor. That is a one important thing that you should make in, you should imprint in your mind. Now you think of here, first case resistive load. We are replacing pull-up network with a resistive load. This is one arrangement. And the second case, we are replacing the pull-up network with a depletion type MOS transistor. Depletion type MOS transistor. And the third type is we are replacing with a PMOS load. PMOS load connected with the ground or connected with a negative battery. Negative battery. So the third design is always preferable. We can call this as a pseudo NMOS. We can also call this as pseudo NMOS. It is a ratioed logic. Ratioed logic. So this third design you can see, as I mentioned earlier, the total number of transistors required here is n transistor for implementing pull down design and 1 transistor for load. 1 transistor for load. This load, it could be a NMOS, it could be a PMOS transistor. That is, it could be a PMOS transistor, or it could be a resistor, or it could be a depletion type. The preferable device is a PMOS load. So here, when we consider ratioed logic, the maximum output, that is output high maximum output is VDD, because PMOS allows strong ones, that is PMOS passes strong ones to reach at the output. So since it is connected to ground, PMOS is always on, so we get VDD at the output F. Output F. Therefore, V over OH, that is high output voltage, is equal to VDD. Whereas low output voltage, you can see we have resistance effect. Right? Low output voltage, we should think of RP, that is RPN divided by RPN plus RL. So pull down network, this resistance plus PMOS network resistance we have to take into account. So the simple idea is PMOS allows strong ones. So strong one means we get a VDD. It is not providing strong zeros. Therefore, instead of zero, it will give some value of output voltage VOL. It could be a 0.6 volt or 0.7 volt like this. So it provides asymmetrical response. And you please remember, very important concept here. Since PMOS is always on, whenever I give input at this point, that is, I'm talking about the third configuration, this PMOS is always on. PMOS is always on. Here, when I give all inputs are high, the pull down network is also high. What happens? Both are on simultaneously. It is not the case in complementary CMOS, but here there's a possibility that based on the input, both pull down network and PMOS load may get turns on. So which will introduce direct path, which will indicate, or which will introduce static power dissipation. That is a major problem. Static power dissipation, and it is not providing full rail to rail voltage swing. Earlier we have maximum of VDD, minimum of VSS. Now this case we can, for a complementary CMOS, I repeat, complementary CMOS, we can get full to full rail to rail voltage swing, maximum VDD, minimum VSS. But here maximum VDD is possible, but minimum, instead of VSS we get some value, instead of 0 we get some value. So full rail to rail voltage swing is also not possible. We have a static power dissipation, right? It is not present in complementary mass. But the advantage here is reduced number of transistors. Earlier we had 2n number of transistors. Now in this case we have only n plus 1 number of transistors. So the total power dissipation, right? And we can write it as 0.69 RL into CL. So with the active loads, again we can talk about the same thing. These two are active load, and earlier when we connect a resistor, it is a passive load. When we connect a transistor active device, active load, it is an active load, because basically we prefer active loads. Why we prefer active loads means resistor, when we write resistor R equal to rho L by A, resistor occupies larger area. We cannot accommodate larger area in the single chip. Right, nowadays we are working with the 3 nanometer technology. We are packing millions and millions of transistors. Putting a large area resistor is very, very difficult, and that is not good at all. Therefore, we are replacing a passive device with an active device. Instead of a enhancement type load, or instead of depletion type load, we can also use the pseudo NMOS PMOS load. So anyway, mass transistor acting as a load, right? For a load, we want only two out. One is connected with the output, another is connected with the supply. Therefore, out of 3 terminals, 1 terminal should be connected together. So here in this PMOS load, gate terminal is connected with the ground, right? So it is a pseudo NMOS configuration. Now, again, one simple example, pseudo NMOS, right? 4 input NAND gate pseudo NMOS configuration. Instead of full up network, we have only 1 transistor. Whereas complementary configuration, we want 8 transistor. For this configuration, we want only 4 plus 1, 5 number of transistors. So their operation, always remember, high output is possible. Okay, high output is V over H. High output high equal to VDD. Strong one, it allows. Good. But VOL depends on the operation of the transistors. VOL depends on the operation of the transistor. It is not 0, right? Smaller area and load, but static power dissipation exists. Always Do remember. So as a faculty member or as a student, we cannot remember all the points at a time, but key points, some of the important points we can keep in mind. So when we take pseudo NMOS characteristics in terms of different aspect ratio, different sizing, right? Sizing is a major thing. So we have to size the NMOS transistor as well as PMOS transistor, right, accordingly. So since we are doing sizing in this case, it is a ratioed logic. It is a ratioed logic. If you do not concentrate on sizing, then we can say it is a ratioless. But here proper transistor sizing is needed to operate it in an efficient way. So when we consider various sizing, you can see W by L of PMOS. PMOS sizing is one case, sizing 2, sizing 4, you can see variable output response or variable output response with respect to input, because it is a voltage transfer characteristics. Voltage transfer characteristics. So from this you can see sharp response occurs for lower value of W by L. Now, so improved loads. Improved load means pseudo NMOS configuration. The advantage is reduced area or reduced complexity, because we want only n+1 number of transistors for the realization. Disadvantages, it is having static power dissipation, as well as full rail to rail voltage swing is not possible. Automatically rail to rail voltage swing is not possible means noise margin also very less, right? So so alternate approaches, we go for improved loads. So improved loads, you can see the same thing in the bottom we are keeping same 4 transistor arrangement. Upper side you can able to see both transistors. Instead of one transistor, now one more PMOS transistor has been added, right? One more PMOS transistor has been added, because the problem is with the pseudo NMOS is static power dissipation. When all the inputs of the NMOS is on, already PMOS is also on, so direct path exists from output to ground, VDD to ground, VDD to ground as well as output to ground. So to overcome this, we are adding one more transistor. It is an adaptive load. It is an adaptive load. M1 transistor has been added. So whenever the A, B, C, D transistors, that is whenever the bottom transistors on, the output should go, the M1 transistor should not conduct. Accordingly, enable signal is given. So this is one kind of approach in which we can avoid the static power dissipation. Obviously, we should adopt M1 size should be higher than the M2 size. Now, the another load, improved load, you can see it is a feedback configuration based load. Negative feedback configuration based load, we shall say this as a differential cascode voltage switch logic, DCVSL, differential cascode voltage switch logic. So DCVSL logic, again same configuration we are repeating, but one configuration is responsible providing normal output, and the another configuration is responsible for providing inverted output. You can see one is responsible for providing out and the another is responsible for out bar. So feedback configuration, output of first one is connected with the input side of next one. Similarly, output of second one is connected with the input of first one. So differential feedback configuration is connected. So we get differential ended output, out and out bar. So the pull down network can be of any type. Pull down network can be of any type. So now you can see the realization of DC VSL logic for XOR and XNOR gate. So XOR gate, we take A B bar plus A bar B. So where we have A B bar, this is A B bar and A bar B, right? And XNOR gate is AB plus AB bar. So AB is available and A bar B bar is available here, right? So likewise we can implement DC VSL logic. So at the time one is on, another should be in off condition, which will avoid static power dissipation. So DC VSL logic, when we draw a transient response in terms of time versus voltage or voltage versus time, we get the response like this. You can see A bar, AB bar, A bar, comma B bar, and AB arrangement. So 3 different graphs has been plotted for all configurations. So as of now, we talked about complementary CMOS. Followed by complementary CMOS, we taught that is we studied about pass transistor logic. Ratioed logic. Now the third component is pass transistor logic. So pass transistor logic is again very simple design, right? Very simple design. Again, it offers lesser number of transistors. Lesser number of transistors. You can see it is we are operating the transistor as a switch. Whenever the switch gets closed, it will passes the input to the output, or it will transmit the input to the output side, right? So no static power consumption, and n number of transistors are needed, right? Ratioed logic n plus 1. For a pass transistor, only n number of transistors. Now you can see for a pass transistor, this is a simple pass transistor, right? This is a simple pass transistor, right? Whenever my input is high, this NMOS device is on, so VDD is transmitted to X. But please do remember, NMOS is a strong function of zeros, right? Strong NMOS passes a strong function of zero, passes strong 0 but not strong 1. So instead of VDD, what we get here is VDD minus VTN. What we get here is VDD minus VTN. Please do remember, right? So for NMOS, you can say NMOS instead of VDD, NMOS pass transistor, when we give input high, NMOS transistor is enabled. It will not transmit VDD as such. We get VDD minus VTN here. So swing is limited or swing is reduced. Once swing is reduced, automatically voltage swing is reduced means what happens? Noise margin is also reduced. So that is the problem. And you can see NMOS only switch elaborately explained here. VB does not pull here we are giving 2.5 volt, right? So instead of we are not getting 2. Whenever C is 2.5, this transistor is on, but we are not getting 2.5 as such here. Gate questions, if you see, similar kind of questions are asked. So we get in the voltage across the capacitor C here is 2.5 minus threshold voltage. So we get 2.5 minus threshold voltage. So threshold voltage loss causes static power consumption. And NMOS has higher threshold than PMOS. Normally, of course, we know due to body effect. And to implement this, it is connected in turn with the inverter device M1 and M2. Now, so we go for, that is the problem with the pass transistor is a simple arrangement, and it is not giving a full output. The voltage swing is limited. So to improve this situation, what we can do, we can go for different solutions. So one such solution is level restoring transistor. Level restoring transistor. So level restoring transistor, you can see here, level restorer, normal pass transistor Mn, and this is a inverter. This is a inverter. Now, whenever B is high, output A is transmitted to X, right? That is VDD minus VTN is transmitted to X. For example, my A is 0. A is 0 means here I'm getting 0, right? A is 1 means instead of 1, I'm getting some 0.5 or 0.6. So it will not change the performance of the circuit. So what you should do, we have to restore the particular value at the output. What we can do is we can connect one transistor here. One transistor here. For example, X here is 1 means out here is 0. Out here is 0. So the 0 is in turn connected with what? See, very simple idea. When B is equal to 1, B equal to 1 means M1 transistor is an on. So instead of A here is assume VDD. Instead of VDD, we are getting VDD minus VTN at node X. So since this VDD minus VTN is very high, after after inverter, we get 0 output. This 0 is connected with the PMOS device. So this PMOS level restorer turns on. So turns on means what happens? It will give a full voltage VDD at the output voltage, right? Instead of VDD minus VTN, now VDD is restored by using the level restorer circuit. That is the idea, right? So full swing is possible. Restorer adds capacitance, takes away pull down current at node X, and we also, of course, we do have a ratio problem. We have to choose appropriate sizing for the restorer circuit as well as pass transistor circuit. So every approach we propose, all is not roses. We do have some advantage, we do have some disadvantages. And next solution you can see, we can take a multiple threshold voltages. Multiple threshold voltages, you can see single transistor pass gate with VT equal to 0. VT equal to 0. So if we take one transistor threshold voltage 0, another transistor threshold voltage normal level, and when we reduce the especially pass transistor threshold voltage 0 means after passing through the pass transistor we get VDD minus VTN. If VTN is 0, automatically we get maximum voltage VDD. So that is also another approach. So by setting different threshold or multiple threshold, especially for the pass transistor, gate voltage, pass transistor threshold voltage is taken with 0, right? So in such cases, we have to think of leakage currents. We have to think of leakage currents because when threshold voltage is 0, when VGS equal to 0 and below, what happens? Sub-threshold leakage current comes into the picture. So all those things are taken into account. So that is a second solution. And the next thing is, next approach is complementary pass transistor logic. So earlier we had simple pass transistor logic. Next approach is complementary pass transistor logic. So for a complementary pass transistor logic, what we do, at a time only one transistor provides output, another transistor, another configuration provides its inverse output. So that is also possible. So we can say this as CPL, complementary pass transistor logic, CPL. So you can able to see the configuration and NAND configuration, or NOR configuration, XOR, XNOR configurations. All of them you can analyze with the so-called truth table. You will get answers. Now, the yet another solution, we go with transmission gate. Transmission gate. So pass transistor we have started. Pass transistor problem. Pass transistor is good. It is offering lesser area, lesser complexity, good. But the problem is it is not providing full rail-to-rail voltage swings because we are having VDD minus VTN. VTN drawback exposes a noise immunity problem, right? That is noise margin problem. Therefore, we go for several solution. One such solution is putting a level restorer. Another solution is putting a different threshold. Particularly for pass transistor, we are putting threshold voltage is 0. And third solution is we can go for transmission gate arrangement, TG, transmission gate arrangement. That is, we are combining both NMOS as well as PMOS together in parallel, right? You can see the bottom transistor is a NMOS transistor. Bottom transistor is a PMOS transistor, pull down, pull up network. Upper transistor is an NMOS transistor, right? We are just combining or we are connecting these two in parallel. So whenever this C, we can say it is a control input. Whenever C is high, A is transmitted to the B side. A is transmitted to the B side, right? Whenever C, for example, when C equal to 2.5, here it is given, C equal to 2.5, C bar equal to 0. C bar equal to 0 here. So C bar equal to 0 means both gets enabled. We get 2.5 as output. 2.5 is out and 2.5 is an output because both are working at a time. Both are working at a time. So what happens? We know NMOS passes strong zeros, PMOS passes strong ones. Since PMOS is also enabled, it is passing 2.5 voltage to the output side. So the capacitor charges up to 2.5. So full swing is possible with the transmission gate. So this is a symbol of transmission gate. Remember, it is like a very, very easy symbol. Simply using triangle, you can connecting two triangles, you can form a transmission gate. Now, the resistance of transmission gates is also taken into account when we analyze the propagation delay as well as speed of operation. So when you talk about resistance of the NMOS, we have this variation with respect to V out, and PMOS it is inverse behavior, and parallel combination almost it is that is nominal. And we can also implement multiplexer using transmission gate. You can see the TG means transmission gate multiplexer. So the transmission gate here is A into S plus B into S bar. The function, if you write A into S plus B into S bar, that is a function of the multiplexer, right? Apart from inverter, we have this multiplexer arrangement using transmission gate. We can write A into S plus B into S bar by choosing select line as 0, select line or control line, you can say. So by choosing respective values of S and S naught, we get one of the signal gets transmitted at the output side. So the transmission gate XOR operation is also possible. Here transmission gate XOR operation, here we are having control signal with P and V bar. Now, similarly, we can also implement full adder circuit using transmission gate. Most of the research papers, you can see there are several approaches for designing adder circuitry itself. We may think that adder is a simple device, but when you realize it in practical way, it is having a lot of approaches are existing in research. So we have separate circuitry for sum generation as well as separate circuitry for carry generation. And so with this static CMOS configuration is over. That is static CMOS. We studied about especially complementary CMOS configuration, then ratioed logic, pseudo NMOS particularly, and then we have pass transistor logic. In the pass transistor logic, we have several approaches using level restorer, using CPL logic, using transmission gates. And next thing is dynamic logic gate. So dynamic logic gates very simple, right? So dynamic logic gates involves capacitance storage, that you should remember. So static circuit, at every point in time, output is connected either to VDD or ground, right, via low resistance path. As I mentioned earlier, the number of gates required to implement static CMOS is 2n. 2n. Dynamic circuits rely on the temporary storage of signal values on the capacitance. I'm repeating the same statement, right? For the dynamic circuit, we have this is for static complementary circuit. Static complementary CMOS, we have 2n number of transistor, whereas ratioed logic and pseudo NMOS, like pseudo NMOS fast transistor gets reduced, right? So dynamic circuits rely on temporary storage and signal values on the capacitance. So basically we have that is basically we need n plus 2 number of transistors, that we will see with the help of diagram, right? N plus 1 number of n plus 1 n type transistor and 1 p type transistors, put together we get n plus 2 number of transistors. That involves the construction of a dynamic logic circuit. So for a dynamic logic circuit, you can able to see very importantly two things. One is two phase operation. One is pre-charge phase and evolution phase or evaluate phase. So two phases are very, very important in dynamic logic gates. So here you can see pull down network requires n number of transistor. Bottom, this ME transistor requires one NMOS transistor. So it is n plus 1 plus the PMOS transistor is here available here. It requires another transistor. So totally we have n plus n for PDN, 1 plus 1. So we get n plus 2 number of transistors required for implementing a dynamic logic gate. Now, two phases pre-charge, clock equal to 0. Now you take clock equal to 0. What happens? This MP transistor is on. MP transistor is on means it is pulling the value supply voltage VDD to the output. So capacitor CL charged to a maximum voltage of VDD. Maximum voltage of VDD. This we call it as pre-charge phase. Pre-charge phase. Now, when evaluate phase, clock equal to 1. Clock equal to 1 means this is off. The MP is off and ME equal to on. And depending on the input configuration, the output is discharges through the pull down network and ME transistor. Right? Discharges through the ME transistor and pull down network. Suppose all inputs of the pull down network are on. All inputs are on. Then what happens? The VDD voltage stored in the capacitor is discharges through the pull down network as well as clock. If all inputs are 0, then pull down network will never turn on. This voltage is kept as such in capacitor CL itself. So this is how the two-phase operation carried out in dynamic logic gate. So one simple circuitry is given. This is A plus, that is AB plus C whole bar. AB plus C the whole bar function is implemented using dynamic logic gate. We have to add both clock timings also. So you can see the function AB plus C whole bar operation using this dynamic logic gate. So when this is on, MP is on, ME is off. When MP is, look at green color, MP is off, ME is on. So at a time only one transistor gets on. So it avoids static power dissipation. No static power. Static power means direct path exists from this VDD to ground, that you remember. Here no static, that is no direct path exists from output to ground or VDD to ground. Therefore, this avoids static power dissipation. Also, this dynamic gate configuration reduces the complexity. So some of the conditions on output we have to think of. Once the output of dynamic gate is discharged, it cannot be charged again. That is, we have to recharge once again. That is, charging, discharging happens again and again, right? So once discharging happens, again we have to excite this with a low input, then only pre-charge happens. So these are some of the conditions, right? Once it is discharged, the charging is happening again until the next pre-charge operation, right? So, and the inputs to the gate can make at most one transition during evolution. So outputs can be in the high impedance state during and after evolution operation, and the state of the operation is stored in the capacitor CL. Now, some of the properties of dynamic gates are given here. As I mentioned earlier, the logic function of the dynamic gates can be implemented using n plus 2 number of transistors. For a complementary CMOS, we have 2n number of transistors, and here we have full voltage swing is possible. Maximum is VDD, minimum is ground. But it is not the case for ratioed logic, right? And we can also offer faster switching speed because reduced load capacitance due to lower input capacitance, reduced load capacitance due to smaller output loading, and no short circuit. As I mentioned earlier, remember, no short circuit current. So all the current provided by pull down network goes into discharging CL. Overall power dissipation usually higher than static CMOS, and it offers low noise margin. When we examine complete circuitry, it offers lower noise margin. So one of the important requirement is it needs a pre-charging and evaluation clock. We have to give a separate clock for pre-charging as well as doing evaluation operation. Right. So some of the signal integrity issues present in this dynamic logic gates, when you see, one is charge leakage problem. Charge leakage problem means you can see the diagram. That is, whenever clock is low, this MP, when this MP is on, so capacitor CL is charged to VDD. That is okay. That is, during pre-charge phase, capacitor CL is charged to a maximum of VDD. Now, what happened? This charge stored in the stored in the capacitor. Suppose if the device is on, pull down network is on, what happened? There is a possibility that it may discharge through the pull down network. It may discharge through the pull down network, right? So in order to overcome this problem, what we can do is we can connect one back to back connect diode, or we can say we can connect one reverse biased diode. So whatever charge leakage, that will go to the diode, right? So now you can see the charge leakage problem. Instead of getting maximum or minimum output, we have charge discharge like this. So major problem with this arrangement is a subthreshold current. Now another solution, one of the solution to this charge leakage problem is like the so-called level restorer. We can also put a level keeper or bleeder transistor. This is a keeper transistor, or we can say bleeder transistor, right? That is, it has to maintain the voltage high always in the pre-charge phase. It should not degrade. So in order to maintain the voltage at a higher level, we can use a bleeder transistor or a keeper transistor. It is like a level restorer circuit in pass transistor logic. Now, another issue is charge sharing. Another issue present in the circuit is charge sharing. So charge sharing means here, remember during pre-charge phase always CL is charged to maximum charge with VDD voltage. Now even during low to high transition, what happens? This transistor gets on. So there is a path exists from capacitor to another transistor capacitor. So what happens? This charge gets redistributed to capacitor CA, leading to reduced robustness, right? So that this is also one of the signal integrity issue present in mask design, particularly dynamic logic gate design. And the charge sharing example is also given. In this case, we have to analyze all cases. When del V out less than VTN, what happens? Del V out greater than the threshold voltage, what happens? So all these mathematical analysis we should remember. So mathematical analysis, please do remember the important thing for a MOSFET, the region of operation you should remember. Saturation region of operation equation, non-saturation region or triode region or linear region operation you should remember, right? So whenever VDS greater than, as far as NMOS device is concerned, VDS greater than VDS sat, we should say MOS device operates in saturation region. VDS less than VDS sat, MOS device operates in non-saturation region. So those things are fundamental things that we should remember while analyzing any kind of circuit. Now, this problem is charge sharing or charge redistribution. To overcome this charge redistribution, what we can do is we can again use a transistor. This transistor is connected with the one of the pull down network device. You can see pre-charge internal nodes using clock driven transistors, right? So this transistor earlier it has been connected with the output. Now it has been connected with, by doing so, the voltage level gets maintained at the output node. So the another thing is backgate coupling. Another issue present in the dynamic logic gate design is backgate coupling. Backgate coupling means here during low to high transition at the in, let us take here in, due to low to high transition, there is a possibility that the out to may vary. Once out to may vary, it is in turn connected with the gate and drain terminals of the previous transistor. So what happens? This out one also varies. Out one also varies because we have a capacity coupling exists between all the transistors. Capacitance coupling is present. If you notice, the capacitance is present, right? Due to the capacitive coupling or backgate coupling, it will affect the voltage value. Affect the voltage value. That is the major problem. So backgate coupling effect, you can see instead of getting exact output waveform, we get reduction in output voltage. So another problem is clock feed through. Clock feed through. Now you can see between clock as well as the gate terminal, gate source of the MOSFET, we have a parasitic capacitance. So because of this capacitance effect, we may have variation in the signal output or variation in the output waveform. So clock coupling between out and clock input of the pre-charge device due to gate to drain capacitance. It is capacitance play a vital role, remember. So voltage of out can rise above VDD, so which will affect the performance of the dynamic logic circuit. So clock feed through effect, you can see we have a peak and undershoot, that is overshoot exists at the top and undershoot exists at the bottom. That will affect the operation of the circuit. It is not an exact waveform because of clock feed through. We have variation in the output waveform. Now, instead of these effects, we also have capacitive coupling, substrate coupling, minority carrier injection, supply noise. So all these problems exist in dynamic logic gates, right? So we can also go with the cascading dynamic logic gates. dynamic logic gates, we can as such we cannot go, because it will affect the that is, change in one output might affect the second stage output also. So we should think of all the variations while connecting cascade dynamic gates. So particularly, that is, direct coupling will involve several effects. So we go with so-called what happens, domino logic, right? So previously you can see direct connection involves several transition. So only 0 to 1 transition provides a good output. 1 to 0 transition varies the performance of the circuit. Now um, uh, the cascading connection, we can go for one simple approach called domino logic. Domino logic means simply, this is one dynamic gates, this is another dynamic logic gate, we are adding one inverter, that's it. We are adding one inverter, right? And to restore the particular output, we are using key per transistor or bleeder transistor or level restorer transistor. That is a very simple arrangement, right? So domino logic, very very simple, both transitions are allowed. So this domino logic, um, for cascaded configuration, we normally go for domino logic in order to have both low to high transition as well as high to low transition without any performance degradation, right? So properties of domino logic, you can say, since we are putting an inverter, only non-inverting logic can be implemented, right? That is a simple thing that you should remember. And it offers very high speed. Static inverter can be skewed only low to high transition. Input capacitance also reduced, which will reduce the logical efforts, right? And while designing with the domino logic, we should think of adding an inverter between dynamic logic gates. So if necessary, we can put the so-called evolution transistor. If for a design, you can see here, the output of the inverter is connected with one of the pull down network. So in such cases, ME transistor need not required. So it can be eliminated depending on the operation. So now next thing is NP-CMOS. NP-CMOS. So NP-CMOS means both pull down network is also possible, pull up network is also possible. You can see pull down network in dynamic logic configuration. This is pull up network in dynamic logic configuration. This configuration we can say NP complementary MOS transistor arrangement. So now next part, so as a combination logic design, we have discussed about all things, complementary CMOS configuration, pass ratio, that is pseudo NMOS logic, then pass transistor, transmission gate, dynamic logic gate. Cascading of dynamic logic gates involves domino logic configuration. Remember these things, very important. Now let us look into the quickly look into the few things related with the designing sequential logic circuit. It is a big topic, so I'm simply winding up with a few slides of sequential logic circuits. So designing sequential logic circuits, you can see we basically have latch and register. Latch and register. So always latch is a level sensitive device. Register is an edge trigger device. You can say register is an edge sensitive device or edge trigger device. Register is a flip flop, and there are many other naming conventions are available. So you can say registers, we can call it as flip flops. So latch and registers, you can see, of course we may say same, but depending on the clock, it will perform. So latch stores data when clock is low, and register stores data when clock rises. You can see here, latch is a level sensitive. So here you can see this is a clock, and data is entering. Data input, it's a D flip flop. Data is entering here. D flip flop is a delay flip flop, right? So data is entering here. So uh, level, when it reaches the upper level, the output Q also maintain up to high level. You can see up to this high level, the clock output is also the flip flop output is also high. Output is also high. Whereas here you can notice the register, it is a clock rises. Whenever clock rises, then the flip flop output changes. So here first rise, you can see first rise the Q output changes and it maintains as such. Next rise you can see again, next rise it is having, next rise up to this the output is available. Next it will check the rise, where we have rise, here we have rise. Whenever it founds another rise, it look at the data input is low, so the Q output also goes low. Q output is also goes low. So this is how at the edge, positive edge or rising edge or falling edge. Here it is given as rising edge. It may also operate with the falling edge. So edge dependent indicates register, level dependent indicates latch. That is a basic difference. Now latch based design is very transparent. That is, n latch is transparent when phi equal to, that is space phi equal to 0, and p latch is transparent when phi equal to 1. Phi equal to 1. So that we know very well. And some of the timing parameters we have to remember. One is setup time, hold time, and clock to output time. Right? So this is setup time is the time taken for the input before the arrival of the data. Right? Hold time is after receiving the data, how much time the data is available in the register. Right? Clock to output is time difference between the application of clock and the arrival of output. So these are all the major timing parameters that we should think of when we consider the sequential logic case. So as far as sequential logic case is concerned, the hold time, setup time, propagation delay time, all those times we should take care. Right? So writing into a static latch, you can see it is like a simple, it is a so-called transmission gate based mux. Right? Data is transmitted from, that is, whenever clock is high, this data is transmitted to the output side. Right? So it forces the state to output side. That is, these forced into output side. And you also think of that here you can see we have two transmission gates. We are coupling, as well as we do have a feedback in this first case. And the second case, we can have only NMOS, that is NMOS only transistor is also possible. If we take this configuration, we do have a problem, back-end coupling problem, because we are connecting inverse, that is back-to-back inverters, which will create coupling effect. So while designing any circuit, we should think of the back-end effect as well as signal integrity issues. So here it is a simple latch or simple D flip-flop transmitting data D to the output Q depending on the clock input. So likewise, we can also propose a mux-based latches. Mux-based latches is also available when mux select line is 1, D input is passed through the output, the select line is 0, D bar is passed through the output. So we can say negative latch as well as positive latch configuration. The corresponding Boolean expression or mathematical expression, you can see Q equal to clock bar into Q plus clock into N. So likewise, we can have clock based, that is edge triggered positive flip-flop is also possible. So for this, one will act as a master, another will act as a slave. So edge triggered master slave flip-flop is also implemented using sequential logic circuit design. But the thing is, we can construct any flip-flop using a sequential circuit, but all these timings will be taken into account. So SR flip-flop conversion, and the registers, in order to speed up the operation, we go for registers. Insertion of registers, particularly the so-called what we call it as pipelining. So pipelining increases the speed of operation. That is a rough idea. So now you can see latches or registers are inserted between the combinational logic circuits to involve to increase the speed of operation. So pipelining, pipelining meant for, that is whenever A1 plus B1 adder performs A1 plus B1, at the same time A2 plus B2 operation also takes place, A3 B3 operation also takes place. We are doing overlapping operation. That is multiple operations takes place we get speed of operations also increased. So clock speed is increased by involving the so-called pipelining. So these are all some of the topics related with the sequential logic circuit. Now, with this, I will finish my lecture. Let me summarize and then finish. So initially we have discussed about what is electronics and what is all about integrated circuit design, what about analog CMOS and digital CMOS. In particular, in digital CMOS, we have discussed about combinational logic circuit and sequential logic circuit. In combination logic circuit, we have discussed about the so-called, what is that? Complementary CMOS, pseudo NMOS, which includes pass transistor logic, transmission gate logic, and all the issues also we have discussed. Apart from that, in the dynamic logic gates, we do have a main phases, pre-charging phase and evolution phases. We can also cascade dynamic logic gates, but as such we cannot cascade. We do use domino logic principle for cascading dynamic gates. We can also have NP CMOS configuration. Then sequential logic circuit mainly relies on latches and registers functionality. We can implement latches and registers with the help of mux based arrangement. Pass transistor based arrangement is also possible. Transmission gate also can be used for implementing the latch or registers. So some other examples also available. We have that is so called bistable switches, and schemic triggers also comes under sequential circuit. So that's all about combinational and sequential circuit. With this, I will wind up my lecture. Any questions from audience? Please, I'm ready to answer.
Participants kindly ask your queries. Participants kindly unmute and ask
Hello,
your
sir.
queries.
Am I audible?
Yes, ma'am. Yes, ma'am.
Any questions from participants, sir? Otherwise, I will wind up.
On behalf of Department of ECE, MSAJCE, I take this opportunity to propose the vote of thanks to the resource person, Dr. Mariammal. We are enlightened with your knowledge and presence, ma'am. We thank our management, principal, and HOD, ma'am, for their support. With this, we move on to the end of this session. Next session will start sharply on afternoon at 2 p.m. Thank you.
Thank you, madam. Thank you for your
Thank
intro.
you, ma'am.
Nice. On behalf of organizers as well as coordinators, my hearty thanks to head of the department as well as coordinators for allowing me to give a guest lecture on this VLSI design. Thank you, one and all. Thank you. Shall I leave this session, sir?
Yes, ma'am. Yes, ma'am.
Yes.
Thank you,
Thank
ma'am.
you, sir. Thank you, sir.
Thank you, ma'am.